Hi everyone, my name is Anderson Justo. I'm going to present the work Analysis of Voltage per Life with Uprating Technique by the Third Harmonic Voltage Injection. The other authors are Giulio Ferrari and Sergio Kurokawa. The objective of this work is to study the voltage per life along transmission lines operated with the third harmonic voltage injection method. In the literature, transmission line operating, we have the current operating method, which aims to increase the current, but involves some problems like increasing the height of the pylons, increasing the conductors' transversal sections, and using conductor bundle, and etc. Another technique, we have the voltage operating. Use the existing structures, require insulators improvement, increase of the clearances, and could be costly. As an alternative, we have the third harmonic voltage injection operated method, which is based on the voltage operating. It is low cost and allows transmission of bulk power via shorter and less expensive pylons. Here we have an schematic, like we have our 60 Hertz power system, and at the transformers we use a third harmonic generator, like 180 Hertz at the sending and receiving end. The interpretation, how does it work? So when we have a fundamental wave at 60 Hertz, we have this waveform here, and once we apply a third harmonic voltage and we add one curve to other, we have at the peak of this waveform here, we have like reduction, and this would be done at the phase voltage. Because we don't change the line to line voltage, it belongs the same. So what happens, we reduce the peak of the fundamental wave, and once this is done, we can increase the amplitude at the receiving end, so we can increase up to 15%, and we will have this red here, the result of phase voltage, up to 1 pu value. So when this is possible, we can increase 15%, and the best value for the amplitude of the third harmonic voltage generate is 1/6 pu. So here we have the amplitude, and here when we increase by this value. Here we have some the arrangements for synchronize the voltage and phase, and once this condition is done, we can calculate the voltage per life along several line lengths. Here we have a schematic on Simulink. We use the distributed parameters to represent the line sections. Voltage was set to 1 pu at the send and receiving ends. More details you can find in our paper. So we are starting to 200 km up to 600 kilometers for a 230 kilovolt line. So when we have the first line studied 200 kilometers, and we divided the line by 50 and 50 kilometers, and we apply the voltage with the fundamental one and with the THV, and we have also measured here just the amplitude of THV component. The resultant voltage at the midpoint of this line is represented here, so the orange one is the one we want to focus on our attention, so it here gets up to this amplitude here. So when we reach 1.87 PU is the maximum condition that must be achieved. So for this line is we have under the voltage limit, so the THV can be applied. Repeating for the 300 kilometers, we have this voltage, so we are just focused on the orange bars, and we all slightly have surpassed this voltage limit, but it's not a problem because for some for any system we have some voltage limits, like more than 5 or even 10% is acceptable depending on some cases, but considering like more like 5% is okay. So our resulting voltage here would be acceptable. For the 400 we are on the edge of this limit, so almost slightly have surpassed this value here, and these are the pro-life along the line, so we are focused on the midpoint, and the receiving and sending at the sending and receiving end, they have kept the condition. For 500 kilometer line, we have already surpassed this value here, so it reaches 1.5. So our THV technique is not appropriate for this long line here. And finally, for 600 kilometers, this is the pro-life, and we see at the middle, at the midpoint, it ups up to 1.8 PU, and here we have the time domain waveform. As a conclusion, as a short observation, for the amplitudes of the THV generators, we see here that it increases as we increase the line length. So for longer lines than 400 kilometers would be complicated, because it will require some phase synchronization between the generators, and there's another problem with wave dispersion. So it is shown that for lines shorter than 400 kilometers, here this technology could be used with some attention, but you have an increasement of the power sending towards the load in this condition. The conclusions are exactly this. For lines shorter than 200 kilometers, we can increase the power transfer. For 300 up to 400 kilometers, we can use this technology carefully, combined with other compensation techniques. And for lines larger than 500 kilometers, this technology is not appropriate. I would like to thank you, and also to FAPESP, CNPq, Unesp, and GAT, and here all are our contacts. Thank you so much.